Now, bear with me. I think the residents are probably a little bit more familiar with this, but we're just going to go through some just basic physics of a Doppler echo, because I think it's important to understand what our limitations are. Now, just as a reminder, your ultrasound transducer is going to emit an ultrasound wave of a certain frequency, and it encounters a source, which is the red blood cells going in a certain direction. And depending on the velocity and the direction of the red blood cells, they are going to reflect back an ultrasound wave. That same wave is going to be reflected back, but with a shift in the frequency. And that frequency shift is called the Doppler shift. It is dependent on the velocity of red blood cells and the speed of the ultrasound in blood, which is a constant. So, and of course, it's the difference between the transmitted frequency and the reflected frequency. Now, this assumes that you are completely parallel to flow. So the problem arises is if your ultrasound transducer, the angle that you're at, is not parallel to flow. So a Doppler can give us excellent information about hemodynamics, but if you're not parallel to flow, you're very likely going to underestimate your velocities and subsequently your pressure gradients that you are using them to ascertain. So if you take a look here, even with a change in the degrees between 10 and 20 degrees. So we say generally around 15 degrees, if you're off of the angle, it's going to significantly change the velocities that you're getting. So very important that we understand what the limitations are. And also the fact that you're unlikely to ever overestimate the velocities. You're very likely going to underestimate. Now, pulse wave, there are two different modalities of the way that the ultrasound transducer emits and receives the Doppler signal. So with pulse wave, there's a single ultrasound crystal, and that same crystal sends and receives the sound beams. It gives a short burst at a certain frequency, and what we're looking for is specifically at a certain sample volume, what is the velocity there? So this allows us to specify, I want to just look at the velocities in the LVOT. That will be pulse wave for you. And on the GE machines, which is what we have at the institution, that's going to be an equal sign. So whenever you're playing around with Doppler, just make sure if you're using pulse wave, it's with the understanding that you're getting a sample volume at a specific location only. Now, continuous wave is two ultrasound crystals, one to send and the other to receive, and they're both working simultaneously. So it measures all the frequency shifts along that trajectory, which is important in terms of registering the highest flow velocity. So in this case, you're not looking for, you're not going to be able to get specific information about where that velocity is coming from. You are going to get the highest velocity. And that ends up becoming important in disease processes like aortic stenosis, for instance, or if there's a supravalvular stenosis. You want to get the highest registered velocity to see how bad the gradients actually are. So just to give you a sense of how this changes the information you're getting, again, if you have your LV over here and your LVOT, your aortic valve over here, if you put a pulse wave in the LVOT, you're going to get this first signal. That is going to tell you what the velocities are in the LVOT specifically. And if you switch to a continuous wave, you're going to get the Doppler signal at the bottom. It's going to register the highest velocity in that angle, which, as you see, is very, very different than when you're doing the pulse wave. So that will give you the highest velocity, which in this case is because of AS. So using these principles, we can calculate cardiac output.